This is what I ended with last time, that you need to do synchronization, and Java provides various mechanisms for synchronization. So there are synchronized methods, there are synchronized objects, there are locks, and all of them provide mutual exclusion. Right? So, and the way Java does it, it's using an internal queue. Okay, so we'll see that today. Okay. So the question is basically how are these locks and all these things implemented. So that's what we are going to study today. Okay. So the book I'm going to use is this one, and have it. Have any of you seen it? It's a recent book and it's very good. In fact, one of the reasons I decided to give this series of lectures is because I wanted to understand the implementation of locks which are given in this book. So, I mean, it's available in an Indian edition also. You can, it's quite cheap to buy. So, here is our, so first we consider a very simple example, that there are only 2 threads. Okay, then we'll see what to do about more threads. Okay, and we want to implement locks for 2 threads. Okay, so remember that this was an interface class. So, and it provided 2 methods, lock and lock. Now we have to have a class which implements that interface class. Okay, so here is a class, and I am calling it Sequential Lock, and the idea here is that there is a flag. I mean, basically each process has a flag. Okay, each thread has a flag, and what does the lock do? Well, the process is either 0 or 1. Okay, and so basically this sets I and j to 0 and 1, or vice versa. Okay, so so I is one process and j is the other process. Okay, now what does so this one is I because it has got its thread ID and it's either 0 or 1. The other one is j. Okay, what this does is it sets its flag to true. Okay, so basically that means that I want to enter the critical section. Right, that's what it's saying, and then it checks the flag of the other thread. Okay, and if that process wants to wait for the critical section, then it allows that process to go ahead. Okay, that process is not interested, then come out and you have locked, you have got the lock, right? Right, and unlock simply sets the flag to false. That's all. Okay, so is this correct? Is this implementation of the lock correct? Is there a possibility of deadlock or starvation? Correct. Yeah, yeah. So what can happen is both can do this simultaneously. Okay, so while this one is setting flag I, the other one is setting flag j, and now this is waiting for flag j and that one is waiting for flag I, right? So we want to actually prove arguments, use arguments of this kind. So the following things can happen. So there is a thread A, let's say. Okay, it sets its flag to true. Okay, and I mean what this code guarantees is it sets its flag to true. Then after that, it checks that the flag B is false. Okay, and then it enters the critical section. Right. Similarly, what B can do is it sets its flag to true. It checks that the flag of A is false, and then it enters the critical section. So this is guaranteed. So by this arrow I mean that this can happen only after this has happened. Okay, right. Okay, but then we also have the following, that out of these two things, okay, maybe what I said is wrong. No, this should be the other way about. Okay, so basically only after B sets its flag to false will A find that the flag of B is false. Right? So I am sorry, this should be in the reverse direction. So only after it writes its flag to be false, only after that A will find its flag to be false. Right? Okay. So what this means is that okay. So now if we trace through this, so basically either you have no, sorry. One second. How did? No. What? Sorry, I didn't make a mistake. This is correct. What this is after the A reads the flag of B to be false. Okay. Right. How can this be? Okay. So this will be done basically, this will be done when thread B does an unlock. At that point its flag is set to false, right? Only after that A can find this happening. Okay, fine. So now what that means is that there was a flag B is assigned false somewhere, which happened somewhere here, okay, before this. Okay. So either the flag here has been set to false and after that this happens, or flag A has been set to false and after that this happens. Okay. Which means that either CSA happens before CSB or CSB happens before CSA. Right. So that's the property which we want, the mutual exclusion property. Okay. But unfortunately, as we just saw, the following thing is possible, that is A sets its flag to true, B sets its flag to true, A checks its flag, B checks A checks the other's flag, B checks the other's flag, and then you have deadlock. Right. So what we have here is a very simple strategy, and this strategy works actually if the two processes execute this method lock sequentially. If lock and unlock are executed sequentially, okay, then this would be correct. Okay. But in order to make this execute sequentially, you would have to declare this method as synchronized. That's what we saw in Java. You give, okay, and then the question is, how would Java implement this synchronized method, right? So we are back to the same problem again. Here we are trying to actually see how the synchronized method of Java can be implemented. So we cannot use the synchronized method of Java to implement that, right? So therefore, this here we cannot actually rely on this property. So that's why I am calling it a sequential lock. It's a sequential lock, which means that if the sequencing is done, then it's correct. But if the sequencing is done, then mutual exclusion is of course guaranteed. There is nothing to be done out there, right? So that's why this implementation of the lock is wrong. Okay. So the first strategy is wrong. So we'll try a different strategy. Okay. So now here you have a concurrent lock out here. So here is our interface class lock, which has two methods, lock and unlock, and we are trying to implement it using this concurrent lock class. This has an integer called victim. Okay, fine. And what is the lock procedure? The lock procedure, it gets its ID, okay, and declares itself to be the victim. okay, which means it basically says the other process can go first. Okay, and it waits while victim is I. Okay, right. So victim is a shared variable. Okay, it's not inside this method. It's a shared variable between the two threads. Okay, and it is set to. So every process sets the victim to itself. Okay, it says let the other process go first. Okay, and then it waits. So when the other process sets this to sets victim to itself, then the lock is automatically enforced out here. Okay, and unlock does nothing. Okay, right. So the sequence of events which can happen is the following: thread A sets victim to A. Okay, and thread A finds that the victim is actually B. Okay, because in between B has managed to set this thing, and then it enters the critical section. Or thread B sets the victim to B. Thread B finds that the victim is A, and it enters the critical section. Okay. So you also have the following, that when will thread A find the victim to be B? Thread A will find the victim to be B only if it sets victim to A, and after that somewhere in between B sets the victim to B, only then this will work. Okay. So again you have this property is satisfied. Okay. So it's never the case that both processes will be in the both threads will be in the critical section at the same time. So our mutual exclusion property is satisfied. Okay, right. Okay, but what can happen is if one thread completes before the other starts, okay, we have deadlock. So I am saying, so what can happen is that this thing does something, ends. Okay, now the other one starts. The other one sets victim to be B. Okay, and sorry, the other one sets victim to B, and then it's waiting for victim to turn to A. But the first thread is actually not interested, let's say, in using the resource at all. Okay, so then nobody is there to turn this victim to A, and so the second thread, even though there is nobody actually wanting the resource, is actually stuck. Right. So here also, I mean, here you have so this is this lock is interesting because it works when the threads work concurrently, but if the threads actually work sequentially, then it doesn't work. Okay. Whereas the previous thing we saw, it worked when the threads work sequentially, but when they work concurrently, it doesn't work. Okay. So what we need to do is to put these two together. Okay. So that's Peterson's algorithm. Okay. So what does Peterson's algorithm do? You have a flag array and you have a victim. Okay. And you get your thread ID, and the other ID is J, let's say. Okay. You first set your flag. Okay. So you say I am interested in going to the critical section. Okay. But you set yourself to the victim. So you say you go first. Okay. So this is like cake cutting or something, that you always defer to the other. Okay. And then you wait on this condition while the other process has the flag set to J, and I am the victim, I will wait. Right. So if no, this is Praveen's laptop, so he brought his laptop. So tomorrow we will see. Yeah. Yeah. So what this is if the other process has its flag on, and I am the victim, then I wait. Okay. If any of these conditions is not satisfied, namely if the other process is victim, then I go ahead. If other process's flag is not set, that means it's not interested, so I go ahead. Okay. And all the unlock does is set the flag to false. Okay. So now what you can show, so now you basically put together the correctness argument of both of them. Okay. and you want to argue now that, so basically there will be no deadlock. In both cases, the deadlock cases which we had earlier, they are both removed. But now we want to guarantee that this is still correct. Okay. So how do we show that this is correct? Okay. So what is the sequence of events? Thread A sets its flag, then thread A sets itself to be victim. Okay. Then it checks the flag of B. Okay. Then it checks victim. Okay. And then enters the critical section. Okay. Thread B also does all this. Okay. Supposing it happens that both processes are in the critical section. Okay. Suppose that is that. How can this happen? Okay. So for instance, that this can happen. Okay. That B sets victim to B and then A sets victim to A. I mean, one of them will have to happen first. So suppose B happens before A. Okay. But if A sets victim to A, then A will read the flag of B as false. I mean, sorry, how does this happen? Yes. Yeah, if A sets victim as A, then that is followed by A reading the flag of B as false, right? So what this implies is B sets its flag to true. Okay, only after that it can set victim to B. Okay, and after A finds the flag of B to be false. Okay, but A never touches the flag of B. Okay, and B, once it sets its flag to true, it will set it to false only in the unlock. Okay, so both cannot be in the critical section simultaneously. So that's a contradiction. Okay, so what we have is we assume that both are in the critical section, and we prove that this cannot happen. We get a contradiction, and therefore this cannot happen. So Peterson's algorithm guarantees deadlock freedom. Okay, and it also guarantees the mutual exclusion property. This is a very clever algorithm implemented by Peterson. Okay, but as you can see, this is works only for 2 threads. Right? In fact, it very cleverly uses the fact there are 2 threads, because you check first yourself and then you look at the other guy, right? So how will we generalize this to n threads? Because in general, of course, there will be more than 2 threads. Any ideas on this? You did the cake cutting algorithm, right? Earlier on. I think Ramanujam probably did that, right? That there also you have a similar thing. Yeah, there is a very simple cake cutting algorithm for 2 people. Okay. Then you want to do a cake cutting algorithm for n people, so you have to generalize. Right? So you have to use some similar idea out here, because that also relies on exactly in the cake cutting algorithm, you cut the cake and then you offer the piece to the other person. Right? You say you take the whichever piece you want. This Peterson's algorithm also it's almost the same idea. Okay. First you set your flag and then you say okay, you go first. I'm going to be the victim. So among the n threads that we have, you will have to impose some kind of data structure. Okay. Only then it will work correctly. So what kind of data structure will we have?
All n-1 are interested to become the victim.
Okay.
Size of n.
Yeah.
So if all the other n-1 threads are interested to become the victim, I will enter critical section.
Correct. So that's the algorithm. Okay. that's the level n algorithm. So, what is this? Oh, I missed this slide. This is showing that in Peterson's algorithm there cannot be deadlock. Okay. So in the previous slide I showed that there is mutual exclusion, but I have to also show that deadlock cannot happen, and it's a similar argument by contradiction. I say that suppose there is deadlock, and I show that there is a contradiction, basically using the fact that victim has to be either I or J. It cannot be both at the same time. Okay, that is what gives you a contradiction. So in fact you get starvation freedom, which implies deadlock freedom. Okay. So Peterson's algorithm implements mutual exclusion without deadlock or starvation. Okay. And this is Peterson's algorithm for n threads. Okay. So we have an n element array, that's exactly what you are saying. Okay. And the level, so this level basically goes from whatever 0 to n minus 1 or something like that, and the level indicates the highest level that thread A is now trying to enter. Okay. So each thread must pass through n minus 1 levels of exclusion, and then it enters its critical section. Okay, right. So at every level what it does is it filters out one thread which is the victim of at level at that thread. Okay. So then n minus 1 become victims and 1 is left, and that process then goes ahead and accesses the lock. Okay. And by using just ordinary mathematical induction, we can argue that this algorithm correctly provides mutual exclusion without deadlock or starvation. Okay. But of course this nobody uses, right, because it's just a lot of work for to go through to set up this entire mechanics. Okay. And this is just too inefficient for actual use. Right. So the question is, can we do something better than this? Right. So Peterson's algorithm is correct, and for 2 threads it's probably it's a very good algorithm. Okay. But in practice, of course, there are never 2 threads, there are lots of threads, and the n level generalization of Peterson's algorithm is extremely inefficient. Okay. So you want something better than this. So another way of trying to improve this is here we have used this array data structure. Okay. So maybe you use some kind of tree data structure. So if you use a tree data structure, you basically set up a tournament. Okay. And at each level, so you have log n levels instead of n levels. Okay, which you go up and you keep on knocking out victims, and until you reach the top, and at that moment you get. So that can be a little better in terms of running time. It might be a little better if there are more threads, but again then there is this overhead of maintaining this huge data structure. Right. So nobody in practice does this. Okay. So this is Leslie Lamport's bakery algorithm. Okay. For implementing mutual exclusion among n threads. Okay. Okay. So Lamport called it bakery because I mean this is how bakeries used to function in those days. So, and we see this today also. So essentially the idea is this, there is a token. So I mean this is what, if you go to a bank today also this happens, right. You go there and you get a token number, and then you are called when your token number comes. This is the essential idea. So he said when you went to a bakery, and there are so many customers in the bakery that they would give you a token. Okay, and then you would be served. So that's exactly the idea out here. Okay. So you get your thread ID, you set your flag, okay, and you get a token number. Okay. What is the token number? You look at all the tokens which are at present existing and add 1 to those. Take the max and add 1 to them, right. So that's your token number, right. So then you basically just wait. So what you are doing is, if my flag is set, okay, and if there is some k, so this is checking, so there is a loop, so this is checking that there is some k, okay, whose token number is less than my token number, okay. In that case I set k to 0, okay, which means this loop will continue, okay, otherwise I increment k, okay. So when will I get out of this loop? I will get out of this loop when I have checked that the token numbers of everybody else are more than me, right. So at that point all these flags, so my flag is set and token number of everybody else is more than me. In that case I'll keep on incrementing k, and finally k will reach n and I'll exit. But the moment I find that token number of anybody is less than me, I reset k to 0 and start the loop all over again. Okay, it's okay. So basically the person with the smallest token number, okay, gets through. Okay. Now what can be a problem with this? The problem with this is that exactly when thread I is doing this, okay, thread J could also be executing this exact statement. Okay. So what does thread J do? It gets token 0, token etc., token n minus 1 and adds 1. Okay, so two threads can get exactly the same token number. Okay, even though normally this won't happen, but it's of course possible that this can happen. So therefore it is not enough to compare just the token number with the token number, because two token numbers might be the same, then again both processes will enter the critical section. Okay. So you do you use the lexicographic order, okay, because the thread ID of both will be unique, right. So if you have both have the same token number, then the one with the lower thread ID goes ahead. Right. So okay, so that's the basic idea. So you use the lexicographic order to break symmetry. Okay. And once you have broken symmetry, then your algorithm will ensure that one thread will go ahead, and that thread will get access to the critical section. Okay. And then the next time when you get a number, token number, the important thing about this is that this is always increasing. Okay. So once it's always increasing, next time you get a number, it will be higher. So once it's higher, then you don't have to worry about you will always be after the other threads. Okay. This is a very straightforward algorithm. So okay. But this is also not used in practice. Okay. Why not? Well, first thing is that you have to implement this lexicographic. I mean, it's not as though Java provides lexicographic symmetry breaking, but so it becomes a long Boolean condition basically, right? So it's a little more wasteful than you can make it. The second problem is that these numbers are always increasing. Okay. So if they are always increasing, then somewhere, supposing your word size is whatever 32 bits, so somewhere you will reach 2 power 32 minus 1 or 2 power 31 minus 1, and then you will wrap around, okay, or get overflow error or something like that. Okay. And then your algorithm will not work. Okay. Now you might say, okay, this is like and who's ever going to have that many threads? Okay, but you may not have that many threads, but you may be using this scheme repeatedly, right? So within maybe within a day you make this many accesses to the critical section. Okay. So therefore these numbers can grow. Okay. So then you have to have, but there is a cleverer scheme. The cleverer scheme basically, just as you can take max out here, you can take min of these and say that all the numbers below that are now useless and can be reused. Right. So at some point you can kind of cycle the numbers around. So you can make sure that there is a bounded number which is always done. But now this makes the algorithm more complicated. Okay. So again, okay. So these are the reasons for which, but there is a further reason. Okay. So the bakery algorithm provides mutual exclusion. It has no deadlocks and it satisfies the first come first served property. So it is starvation free as well. So all the properties are okay. And then there are cleverer versions, and there is one by Shiv Shankar Haldar and Paul Vitani, which reuse tokens. That is what I said just now, so that they do not grow unboundedly. Okay. But it is not used in practice, and the reason for it is this: because it reads and writes as many memory locations, okay, as there are concurrent threads, okay, and that number is unbounded. What do I mean by this? See, I have to read all these, no? Token 0, token 1, I have to read n locations to actually find this and add 1, and in general I will be writing into n locations also, right? So therefore you are doing reads and writes on n locations, and if the number of threads is extremely large, say there are 10,000 threads, okay, then you have to sit and to find this max you have to read some 10,000 locations, which is too slow. Okay. Right. But unfortunately it was shown by Jim Burns and Nancy Lynch. They showed that any deadlock free mutual exclusion algorithm which does not use any stronger method of synchronization than read and write operations will have to have this problem, which means it will have to read and write n locations, okay, where n is the number of threads. Okay. So they proved a theorem that this is inherent to using reads and writes for synchronizing. Okay. So what this suggests is that you should use something stronger than reads and writes for synchronization. You shouldn't use just reads and writes. That's not good enough, because then if you will always have this limitation that any algorithm you write will, and provided it provides mutual exclusion and is deadlock free, which you certainly want, okay, that will definitely use at least n locations. It will read and write n locations, and so it will be order n time, where n is the number of threads. There is another problem, and this is the, okay, supposing, let us say we have only 2 threads, okay, so we do not actually have, okay, so we implement say Peterson's algorithm, okay, for 2 threads, and we are running it on some multiprocessor, and we run it many times, okay. So for instance, we have some program which enters the critical section exactly 500,000 times, right, okay. What is this counter? Maybe I meant bakery algorithm. Where is the counter in Peterson's algorithm? There is no counter. I think what I was doing is I was doing yesterday one counting algorithm that you are using counter, which you are updating, right, all the time in order to implement mutual exclusion, and that counter, supposing for doing the incrementing the counter, supposing I am using Peterson's algorithm, okay, then if I increment the counter, if I do this in such a way that it works exactly 500,000 times for both, so at the end of that the value of the shared counter should be exactly 1,000,000. right? Because half a million times thread 1 uses it, half a million times thread 2 uses it. Okay, but when you actually run this, you discover that the algorithm is, I mean, that counter value is not 1 million. Okay, it's slightly off 1 million. Okay, right? So there is some small error. It's not very different from 1 million. Okay, but the question is, why is there an error? Okay, because our algorithm is Peterson's algorithm is correct, right? And you have used it to increment a counter 1 million times. The value of the counter should be 1 billion. Okay, why isn't it so? Okay, so basically, what this means is that even though you think the algorithm is correct, it's not actually correct. Okay, it's I mean, at some point, two threads are getting into the mutual exclusion, into the critical section simultaneously. Okay, so how does this happen? So now we have to look at some multiprocessor architecture. Okay, so basically what we assumed is, when I say flag of something I is set to false, then I assume that that is one atomic operation. I set flag of I, it's some memory address, and that memory address is set to false. That's all. Whatever is the bit value false, that is done in one atomic operation. Okay, but unfortunately this is not what happens in multiprocessors. Okay. In multiprocessors, or at least typical multiprocessors today, what they do is they actually put this into a cache, right? So this thing is sent into a cache. Okay, and at some point later it goes from cache to memory, right? So so therefore what might happen is, you might put something in the cache, okay, and then some other value, and then maybe some other value gets put into the cache, or some wrong value happens. So some screw up can happen inside this thing. So which is what gives you that the fact that that number is slightly different from 1 million. Okay, so and then it's also true that sometimes parallelizing compilers, they also sometimes change the order in which things are done. Okay, so although your code looks perfectly correct to you, it looks as though everything will execute neatly, but actually it's executed in a different order. Okay, so this property is called there is a property called sequential consistency. Okay. Sequential consistency is that when you look at the code of one process, and you have first one statement, then another statement, then another statement, you believe that the first statement will happen, then the second statement will, then the third statement. So when you write your program, you believe that it's sequentially consistent, but actually the parallelizing compilers don't guarantee this property. And so things might actually happen in different orders, and when this different order gets interleaved with some different order of some other thread, then something might happen which you never anticipated. Right? So this is actually a problem with modern multiprocessor architecture. So you have to, so of course, I mean, when we write an algorithm, we are not expected really to think of all this, and we expect a sequential consistency property, but when Java provides a feature like locks, they can't say that we didn't know this. Right? So they have to make sure that all these things are guaranteed. Okay. So we'll now look at this synchronization primitives which use an instruction called test and set. So you are no longer using just reads and writes. Okay. If you are using only reads and writes, then there was that theorem by Jim Burns and Nancy Lynch, which showed that you are forced to do reads and writes of at least n memory, order n memory locations, where n is the number of concurrent threads. Okay. But now we are using a more powerful instruction, test and set. Okay. And with this instruction, that theorem no longer applies. Okay. So maybe you can do better. That's the idea. So, and so test and set is whatever. Right. So this is for a bit. So intuitively you can think of test and set as being something like this. Yeah. So it's basically an if then else, right? So this branch, so if B is false, then B is set to true, otherwise nothing happens. Right? So you test B and you set it. I mean, that's what test and set is. Okay. And there is one hardware instruction which does this. Okay. So it's an atomic instruction. This is guaranteed. Okay. So we expect that, but of course even this instruction, okay, if it goes through cache, okay, then this won't be atomic. Okay. So Java provides a class called atomic boolean, okay, which guarantees that this instruction is executed atomically. Okay. So similarly, there is atomic integer and atomic other types. Okay. So you can do, for instance, if something like, in the case of an integer, you can do something like that. Yeah. So test and set allows you to check that some value, and only if that condition is satisfied, then it works. Okay. That's what it says here. So there is a set B method, which just whatever value B you give, that gets stored. Okay. Oh, so this is slightly different. This is a get and set B. Okay. So what get and set B does is, okay, is that in the location, in that location, okay, this value B is stored, okay, and whatever was the value is the return value of this function. Okay. So I am saying, so if I say get and set true, okay, what this says is store, keep this as true, okay, okay, but in order to check that this is actually this was actually the case, so you check this. Okay. This, because you get the old value back, you check that that was false. Okay. So what this says is, while the okay, so if the old value was false, okay, then you set it to true. Okay. Otherwise what? Otherwise the old value was true, so this will be false. So if I write a loop like this, So this loop is actually the same as executing test and set, right? Right? Because you exit this when the old value was false. Is that correct? Let me check. No, it's not while. I think it's if. Yeah, this is okay. Yeah. So what this says is if the old value is false, then it is set to true. Okay. So if the old value is false, then it is set to true. Else nothing happens. Else the old value is true and it's set to true, which means nothing happens. So this if, okay, is the same as test and set. Okay. So you can implement test and set using this get and set. So this is what is provided by Java. And now you have an implementation of the lock. So there's basically this atomic boolean. So there's a bit called locked. Okay, it's initially set to false. Okay, and what does the lock method do? The lock method waits until this thing succeeds. Okay, so basically it tries to set the bit to true. Okay, so. Okay, once it succeeds, the locking is done. Okay, what does unlock do? It sets the bit to false. That's all. Okay, so it's a very straightforward implementation, and it shows you the power of having an instruction like this. That suddenly something which was taking you a lot of effort earlier. Okay, you have to look at all the threads and all that. Here we are not looking at any other thread. There is just one shared variable, okay, which is implemented in an atomic way, and you just use test and set to set it. That's all. Okay. So once if you use this implementation, you won't get those kind of errors which we saw earlier of the count not being somewhat less than 1 million or something like that. All that will not happen. Okay, but there is a different problem. Okay. And the problem is that as the number of threads using this class increases, the performance drops very sharply. Okay, so I think it's something like this. So supposing this is number of threads. This is, let's say, some time taken or something like that, okay. And the performance goes like this. Okay. So as the number of threads this becomes slower and slower to execute. Okay. Why do you think this happens? See, the kind of problems which we are dealing with. See, what we have done is we had earlier, what we were looking at earlier was we had theoretical problems. We said, oh, we are not getting deadlock freedom, we are not getting starvation freedom, we are not getting mutual exclusion. Now the theoretical problems are all solved. These algorithms are all correct. There is no doubt about their correctness. It's a very straightforward implementation. So all you are doing is using one hardware instruction. That's all. Okay. But now you find that practically these things don't work like the way you want them to work. Okay. So where can the difficulty be? Yeah. So again, the difficulty is in multiprocessor architecture. Right. So we'll do an analysis of this and we'll see how this works. But before that, let me so just look at the code of this. What is the code of this? in a loop you do get and set, that is the code for lock, and this said you just set it to false, right. So just remember this. I will look at a different implementation. So this is called test and set, right. Okay. So all we have done is we have changed this, right, and what do we do? So first we have an infinite loop. I hope it ends somewhere. It ends here. This should be moved. Okay. No, sir. I needed another bracket here. Okay. So you have an infinite loop, and what you do is you don't execute a get and set. You execute a get. You keep checking whether that value of that bit is true. Okay. So when you find that the value of that bit is false, at that point you try to do a get and set it to true. Correct? Okay. But of course this may not succeed, because in between some other process might have set it to true also, right? So if this works, of course you return, then you are out. But if this does not work, you again go back into the outer loop. Okay, this is clear how this works. So what we have done is, instead of doing this inside the while loop, we have an inner while loop which just does gets. Okay, and get and set is done only relatively rarely. Only when you think it's you already have some indication that it's going to be false, at that time you do the get and set. So it has a better chance of succeeding, right? And now if you implement this, the performance of this is something like this. So this is the test and set, and this is test and set. Right? So the performance is much, actually, I don't know, there is no scale here, but basically it becomes much better than test and set, but it still becomes worse. Okay. Right? So this implementation was suggested by 3 people, Clyde Kruskal, Larry Rudolph and Mark Snare. Okay. And functionally there is no difference between this and the previous implementation, okay, because all you are doing is once it is false, you are checking again to see that it's false, and of course since that may be violated, you put one more loop around that. That's all. Okay. But it still slows down as the number of threads using the class increases, but it performs better than the ordinary test and set. Okay. But the question which we need to examine is, first of all, why should there be a slowdown at all? Right? There is no reason for there to be a slowdown. So again we have multiprocessor cache. Okay. So the slowdown in both implementations is due to the cache. Okay. So basically what happens in a multiprocessor, the processor, when it wants some value from memory location, it sends an address, right, and it says give me the value, it asks the memory. Okay. Now it might be that the required memory address is inside the cache, okay, and that we call a cache hit. Okay, and if then the cache immediately provides that value. Okay, so it's loaded immediately. So otherwise we call it a cache miss. Okay, and if there is a cache miss, then there is a bus between the processor and memory, and the processor broadcasts the required address on that bus. Okay. Now all the processors, there is only one memory, so all the processors share that bus going into memory, right? So if another processor has that address in its cache, it broadcasts its value on the bus, and that is what is picked up, right? So I am processor I say I want memory location 1000, okay, but so I don't have it, my cache doesn't have it, but the cache of processor J has it. Then processor J broadcasts that value on the bus, saying here is the value of memory location 1000. Okay. So otherwise what might happen is no processor has the value of that location, then memory responds with that value, and this actually works because the processors are much faster than memory. Okay, so memory is the slowest in this. So the moment one processor sends something, you pick it up. Okay, so the fastest is when you have a cache hit. You can have a cache miss, but a cache hit in another processor, or you go to memory. Okay, yeah. So unfortunately, as I said, do we have to know all this? Yes, we do have to know all this. So I mean, the present state of the art is that we have to know all this. We have to know that, because if you are going to want parallel programs which have good performance, then you have to know that this is how they will function. Okay, which is not an ideal state of affairs, but that is what it is. So here is what happens in this lock. So remember, this was the original test and set implementation, where you do this get and set inside the while loop. Okay, so what happens? Every get and set call has to be broadcast on the bus. That address has to be asked for on the bus. Okay, and all the processors use this bus to communicate with memory. Right. So these calls delay all the threads. I mean, that other processor might be accessing some totally different location in memory, but still that processor cannot use it because this processor wants that location from memory. Okay, so that's the first problem. The second problem is that once you do a get and set, okay, this forces other processors to discard their own cached copies. Okay, because once the get and set succeeds and you get some value, then you have done a get and a set, right? So you set it to something. So if you set it to something, then the cache value which is there in the other processors is presumably wrong. Okay, so therefore that process is forced to throw it out. Okay, but actually we see that this is happening in a loop. Okay, and in the loop, actually while this loop is running, the value is just being read as true and being set as true. Okay, so actually the value is not changing. Okay, so but the other CPU does not know this. The other CPU only knows that some set was done. Okay, so they get a cache miss, and when they want something from that location memory, then they have to again go to the memory, right? So it's no longer in their cache. So this is why when the number of processors increases, okay, so every processor is doing this for every get and set. Okay, so you just keep getting cache misses all the time. Okay, this is what makes this inefficient. And in the other example, so this is in test and set. Now this is a little better because this thing, the first time you get the value, maybe you get a cache miss and you get that value into cache. Okay, but now the next time when you do this, it is already in your cache. Once it's in your cache, you just keep getting it. So you once this succeeds, at that point of course there will be cache miss, but this might happen after a long time. Right. Similarly, when you set this, at this point you will get a cache miss. I mean, the other processors will get a cache miss. Right. So that's why this shows that test and set will be more efficient than test and set. Okay. So that's what is explained here. So if thread A holds the lock, then the first time thread B reads the lock, it takes a cache miss. But now as long as A holds the lock, B reads, okay, and it always gets a cache hit. Okay. When the lock is released, all waiting threads have to take a cache miss. Okay. But then one of them succeeds and the cycle repeats, and we make it better still. Right. So because so the idea here is, so this idea is due to Anant Agarwal and Matthew Cherian, and what they said is that once you get a get, okay, you know that the bit is locked, right? Somebody else has locked it. So should you immediately spin again, right? So why not wait some time and then try the spin, right? So this is the idea which these guys used. It's quite a famous algorithm. called exponential backoff. So basically actually it's easier to read this. Okay, so we just use the idea that probabilistic algorithms might perform better than deterministic ones. So, and in particular the Ethernet protocol uses this. Okay, so that's where this Agarwal and Cherian, they designed this for the Ethernet protocol. Okay, so what you do is when you get that the bit is locked, okay, then you wait. So let's say you wait for, I don't know, maybe 10 nanoseconds first. Okay, then you check the bit, you get it's locked again. Then you wait for 20 nanoseconds. Okay, then you, and so on. So you keep doubling the amount of time you wait. Okay, and up to some fixed maximum. So you keep. Okay. So then the number of waits you are doing is relatively low. Okay. But this is not what you want to do. Okay, what you want to do is the following. Because the checking that bit is locked is something going to your local cache. So that it doesn't matter if you do a million times. Okay, it doesn't matter. But that get and set you shouldn't do very fast. So once you do the get and set, and you find that its value is false, okay, then that you should do a back off on that. So you should not do that get and set again for someone. When you get that, you should sleep. Okay, that's the idea essentially. So this is the back off class. So this back off method, what it does is it gets a random integer. Okay, yeah. So basically, and a random integer between, I mean, in that within some limit. Okay, and you also change the limit to twice the limit, so that the next time this is called, you will get a random integer which is within 0 and twice that limit, and you take the minimum of whatever is the maximum you have decided and twice the limit, and then you go to sleep for that amount of time. Okay, so that's what this does. And what does the back off lock do? Well, there is some min delay and max delay, and you initially set that. Okay, so while you get so this you would keep on doing because this is for the local cache. Okay, so now supposing the get and set actually succeeds, which means that the old value was false and the new value set is true, then you return. Okay, but supposing this was not the case, you call the back off class. So when you call the back off method, this will delay for some amount of time, and the more times you call this, the delay will become larger and larger. Okay. So as I said, the performance of this is so good that it's actually implemented in Ethernet, this idea. Okay. But Java does not use this. Okay, why does Java not use this? Because you can be still more efficient, right? So the whole game in this is to try and keep improving your algorithms, look at performance, keep improving your algorithm. You just keep on doing this, right? Java uses Q locks. That's what I said right in the beginning. Okay. What are the problems with back off locks? Okay. Back off locks is first that after all you do a back off, which means you delay for some time, right? So it might be that actually the critical that thing becomes unlocked within that period. Okay, so the critical section is underutilized. Okay, so okay, I mean of course our probabilistic algorithm is built with that in mind, that you underutilize. Okay, but why? I mean if you can do it without underutilizations, why give that up? So that's the idea. Okay, and there is also another thing, which is that all threads spin on the same shared locations. All of them are there's that one single lock bit which everybody is trying to access. Okay, so you get some kind of cache coherence traffic on this. Okay, which is, as we saw, it is less than in the case of test and set lock, but it is, but there is still some inefficiency because of this. Okay, so what you want to do is you have threads which form a queue. Okay, and this avoids both these problems. So first thing is each thread will now spin on a different location. Okay, because there is a queue, so this thread will be spinning on let's say its position in the queue, the other thread will be spinning on its position in the queue, and so on. Okay, and secondly, there is no need to guess how long to wait. You don't have to do this back off business, because each thread will be notified by its predecessor in the queue that, look, I have finished with my lock, so now you wake up and you start doing get into the critical section. Okay, and also of course the queue provides first come first served fairness, hence the algorithm is automatically starvation free, okay, and deadlock free, so you get that property free on the house. Okay. But you have to implement the queue, right? Okay, so now all your, so basically now you start using all the knowledge that you have of your data structures and try to implement the queue in the most efficient way that possible. Right. So the first algorithm we'll look at, so we'll look at three algorithms. The first is the simplest one given by Anderson in 1990, okay, and then two more, and we won't actually look at the one which Java uses, because I mean that is more complicated than to explain than here, but we'll look at kind of the core idea of that algorithm. Right. So this is Anderson's lock. Okay, so this uses an atomic integer, okay, like we used atomic boolean before. So this atomic integer points to the tail. Okay, so this shared points to the tail of the queue. Okay, and there is also a flag array, and this flag array is actually going to be the queue. Okay, so basically threads will set their bit saying I want to go ahead, so that will be inside. And the size, and what you say is, to the Anderson lock you give a capacity that I want an array of this many elements, okay, and you create this flag array with that many elements, and you set the 0th element of this to true. So this is just the initialization. Okay. So what does lock do? Okay. So first you look at the tail, you get its value and you increment it by 1. Okay. So this is an atomic integer. So this provides, like it provides get and set, it provides get and increment also as a one atomic operation. Okay. So you get that, you take that modulo size, right? Because there is some fixed size, you rotate from 0 up to n minus 1. Okay, and so that is your slot number. Okay, and you try to set that bit on that slot on your flag. Okay, so essentially what you are doing is the following. Here is your, effectively this is your queue, right? This array is your queue. So tail currently points to this. So you basically get an increment tail. So tail will now point to this. Okay, and what you do is you try to set this bit. That's all that is happening. Okay, you try to set this bit, but of course somebody else could have done this simultaneously, right? No, this is atomic, so somebody else could not have done this. Anyway, you try to set this bit, and if that flag is false, okay, then you wait. So you wait until it becomes true. Okay. what would it mean for this to be false? It means that all these things are actually being used by some other threads. Okay, so there are n threads. How can that be? I don't understand this. Okay, let's look at the unlock. So unlock is you get this index, you get its value. What is my index? Okay. Okay, my index is okay. First of all, it's a thread local variable, which basically means it's not a shared variable. Okay, and it's initially set to 0. Okay, that's what you have. Right. So basically this is your own, I mean you keep track of what your position inside this thing is. Okay, so you keep track of that. Okay, and you try to set it to the slot value and then wait for that slot to become true, right? Okay, when will it become true? This is when it will become true. When the previous process, okay, when it unlocks, what it does is it gets its slot for it knows what it's slotted is, it sets its slot to false, okay, and slot plus 1 it sets to true. Okay, so it says that I am done with my job, now the next thread can get it. So when this becomes true, then this loop will end and that process will be able to enter the critical section. Okay, so it's just a circular array which we are using. Okay, so of course there is an obvious disadvantage to this algorithm, okay, which is that you need a known bound on the maximum number of concurrent threads, because that array size you have to fix, right? So how will we change this? Yeah. Huh? Using a list, right? So basically pointers. There is no other way to do this, right? Okay, so this is by Craig, Landon, and Hagestein in '93. Okay, so it uses a more usual pointer implementation of a queue. Okay, and now it has, so therefore they have to use some type called atomic reference, which is provided by Java. Okay, just like that one used atomic integer, now you have to use atomic reference. Okay, and I have not shown here the actual implementation. The actual implementation also recycles the queue nodes, but here I'm just using fresh queue nodes all the time. Okay, and on cache coherent architectures, the CLH algorithm has the best performance. Okay, at least in 2008, that's what these guys say. We don't know what is the situation in 2011. Okay. Okay, so it's a complicated algorithm. So, but if you remember the Anderson algorithm, all you have is now instead of the circular array, you have a linked list. That's all. There's nothing else. But the clever thing is how the linked list is maintained. That's all. Okay. So you have an atomic reference type of which points to nodes of type Q. Okay, and that is what tail is. Okay, and you have two thread local variables. One is my predecessor and one is myself. Basically, where am I inside this list? So initially, this tail is created. So one location is set up. Okay, and you get some my node. Okay, which you generate a new node. That is my node. Okay, and my predecessor is initially nil. So this is just the initialization. we look at the lock method. Okay, so lock method first gets the value of my node. Okay, set its so each node has a locked field, so that locked field is set to 2. Okay, now you get the predecessor. Okay, set that to my pred. Okay, fine. And now check the locked field of the predecessor. So the predecessor is this thing. When the predecessor thing becomes unlocked, at that point you can go ahead. What does unlock do? Unlock, gets my node, sets the lock bit to false. Okay, and sets my node to my predecessor. Right. So it's a very clever implementation of queue, because the queue is kind of virtual. There is no actual queue. Okay, so basically each processor just gets creates one node for itself, maintains it while it's locked, and when it's unlocked, it removes that node and quietly disappears. That's all. Okay, and sets it to point to my predecessor. Okay, so each thread status is in a queue object. If its lock field is true, then either the thread has acquired the lock or is waiting for the lock. And if the locked field is false, the thread has released the lock. That's all there is to it. And you just look at the predecessor and you work like. Okay. So look at this. So this is the thing which will be happening most often, right? Because this is inside a loop. So you are looking at pred.locked. Okay. Okay. What is pred? Oh, sorry, no. Predecessor is here. So predecessor is you get from the tail. Okay. So predecessor you get from the tail. So you do a get and set once. Okay. So you get this predecessor, but this is now a local variable on which you are spinning. Okay. So you are only all the time you are testing your local variable. Okay. So only once when you do this lock, you get the shared, you touch the shared variable, because that's when you are modifying the tail. Right? That's the only thing you do. Yeah, so that's what is said here. Each thread refers to its predecessor through a thread local pred variable, and the tail field is public and has the node most recently added to the queue. The tail field always points to that. So finally we come to this Miller-Crummy and Scott lock. So basically, so this is the idea which is used by the Java virtual machine. Okay, it's not exactly this algorithm, it's more optimized version of this algorithm. Okay. So I said in the previous thing that CLH algorithm is actually faster than this, right? It's the fastest known. So why don't we use that? I mean, why doesn't Java use that? Because it's faster for cache coherent architectures. Okay, but Java can be used on any kind of architecture. Right? So they have to choose some algorithm which works on an average better on all kinds of architectures. Okay, so that's why they use this algorithm. And I mean, I'm not even sure that. I mean, they keep changing and getting better versions. For instance, they use some ideas from this. Recently, I think they've tried using a composite algorithm, which takes 2 or 3 algorithms and tries to do some clever mix of them. Okay, so Algorithms keeps changing, but here is the key idea. So this is again a simple Q lock algorithm, but this is more complicated than the CLH algorithm. In the CLH algorithm, there was actually no queue; it was a kind of virtual queue. Here, there is a real queue, and that's the only difference that you will see. So you have tail, my node. So let's get to lock. Okay. So you first create a queue node, then you get the predecessor from the tail. Right? From the tail you get the predecessor, and you set your node to the current tail, which basically says that I want to access the critical section. Okay. Then if the predecessor is not null, which means that there is a predecessor, okay, then you want to point the predecessor to yourself. Okay, so that's what is done here. Okay, you set pred dot next to your current node. Okay, of course you set it to lock, which is what you want. Okay, and then you have to wait. So the predecessor, and now you wait until this is locked. Okay. Okay. So when will you get out from this? Okay. So again the idea is the same. To acquire the lock, a thread appends its own node at the tail of the list. Okay. So unlock is more complex. Okay. So you first get whatever is your node. So this is your own node. Then if this does not point to anybody, that means you are the last. Okay, that means nobody else is waiting. Okay, then basically you want to return. Okay, so I'll just explain this in a minute. Otherwise, what happens? Otherwise, there is somebody waiting. So you have to wait for the predecessor to fill the next field. Okay, so the predecessor will. What we got here. Q dot next was not null. No, sorry, was null. Okay, that means that there is nobody else waiting. Okay, so you wait until somebody else is waiting. Somebody else wants the thing. Okay, and that at that point you set this thing. Okay, so Q node dot next dot locked is set to false. Q node dot next is set to null. Okay. So one thing is that while unlocking. Here you check that there is no one else waiting, okay, but there may be some thread which is just trying to get attached to that. So you that case, and for that you do this compare and set. So this compare and set is again an atomic operation, and this is sure that there is actually nobody waiting. Okay, and then you can return. But if there is somebody else waiting, then you have to wait for that thing to appear, and you have to set it to. This is what you okay. So we have looked at basically a few things. We looked at contention, and then we looked at general resource sharing ideas, in particular mutual exclusion. Done using locks. Okay, so here doing this I use something called semaphores. Okay, so one exercise is to see how semaphores can be implemented using locks. Okay, so if you have locks, you can implement. Okay, the converse locks both are, but Java has chosen to use locks. Okay. And then we looked at the implementation of this. So basically there are many kinds of locks. So in particular we looked at what the Ethernet uses, which is an exponential backoff lock. And we looked at Q locks. Okay. Earlier we looked at some kind of theoretical locks like Peterson's algorithm or Lamport's bakery algorithm, which are good in theory but don't work in practice. So these are all very active areas. So I mean, people are all the time trying to improve these things. I mean, there is also a certain amount of prestige associated with the fact that it's your algorithm which is being used by Java or some programming language. So people try very hard to get more and more efficient things done. But in some, I would say that this takes care of handling concurrency on a multiprocessor system where the memory is shared between all the processors. Because the crucial difficulty there we identified, whatever you do, ultimately it comes down to some mutual exclusion property, and somehow you have to implement this. So locks is one way. Then how do you implement the lock? Okay. So now you saw here that this is an implementation of a lock. It's done in a very careful way, taking all kinds of architectural parameters into account, and it works on the average. It works efficiently across all architectures. Okay. So this is the thing which, I mean, or something based on this is what is used these days. Okay. But there is also a different kind of architecture, okay, where, I mean, you have one multiprocessor and you have one multiprocessor. This has memory and this has memory. Okay, but they have their own local. There is no shared memory. Okay, and communication between them is by, I don't know, some wire or wireless or whatever, right? And this is not using the memory of the system upstairs, right? This is communicating. Okay. So the question which I want to tackle now is, how do you actually implement this kind of code? How do you implement a distributed algorithm, say Dining Philosophers or something, when because we know that for Dining Philosophers, at least asymmetric, there is a truly distributed solution. Right. So how is that actually implemented on when there are actually lots of processors sitting in different locations and which communicate only through wires, and there is no shared memory for you to work with. So we are moving now out from this kind of world, which you might say is the classical world of operating systems, into the world of networks, where now you have things situated in different parts and you have to communicate bits across that. Okay. So I'll try to do that tomorrow. Okay. Thank you. So okay, here's a simple question. What is the difference between these two kinds of things in computer science terms? Okay. What does that mean? What is synchronous and what is the meaning of asynchronous? Yeah. Okay.
And asynchronous, you wait for the other person to send reply, then you reply.
Okay, that's fair enough. So which is better?
Depends on what you want.
Well, basically message passing, let's say there's some information you want to convey, right? I mean, that's one purpose for which we do message passing, right? So which is better?
Because immediately you can find out that he's
You
receiving
get
the
it?
message.
Yeah. You tell him you got the message on WhatsApp.
Okay. How do you prove that? That's related to what you are saying, but I want a mathematical statement. Right? See, all these is not what I do research on. I am basically a theoretical computer scientist, so I do research on things which are mathematical. Right? So I want to ask such a question, then I'll have to pose it mathematically and try to answer it mathematically. I'm just trying to give you some idea of how one does this kind of thing. Right. So supposing you have some information, let's say I, or let's say F, it's a fact. Okay. And this is me and this is you, say. Okay. So when I say that, so let's say I know F at this point. Okay. And then I send this message to you. Okay, so you know F at this point. But there's something more. Okay. You also know that I know F. Okay. But I don't know that you know F. And that's why I'm trying to send the message to you. And maybe you know, but at least I don't know it. Right. So whatever, let's suppose what Baba Ramdev has been just arrested at Rajghat or wherever. I know this, okay, but I'm not sure whether you know this or not. So I'm sending this message to you. Okay. So how can I guarantee that I know that you know F? Send an, yeah. So once you get this, you send me an acknowledgement. Okay. At this point, I know that you know F. Okay. But at this point, You don't know this. You don't know that I know that you know f. Okay. How will you get to know this? If you send an acknowledgement to this. Okay. So basically kind of nesting this I know you know business several times, I can always find some statement which is true for me but not for you, or true for you but not for me. So it depends on which side you are on. Find such a statement. Okay. Whereas if call, okay, then this, let's I say whatever, something has happened to Baba Ramdev, then all these statements become true immediately. Okay. So I know this fact f, you know f, I know that you know f, you know that I know f, I know that you know that I know f, everything becomes true immediately. Okay. So this is a mathematical proof that any number of messages is less powerful than one phone call, okay, for the purpose of conveying information. This is a very old theorem. This was proved in the 1980s. So synchronous message passing, at least some purposes, let's say. Okay. What is the advantage of asynchronous message passing? Basically, you don't have to wait. Right? You just send your message, and some point that person will get it. Okay. But you don't know when, right? And maybe you send it, and that person has forgotten his or her mobile and gone on vacation or something. So you never might get it only after they come back from the vacation. Right? So in that sense, this is not that reliable a medium. I mean, you're okay. You could say it's well, at least that person will get it some, but maybe not. Maybe that mobile gets stolen. Okay, and therefore that message never actually gets to that person, or that person leaves the mobile somewhere, forgets it, something. So whereas when you give that information, after that the phone may break down, the whole phone system might collapse, doesn't matter, but you still, all this, these I know, you know, everything becomes true. Okay, so phone calls common knowledge between the two parties who are speaking. Okay, whereas letters don't give you common knowledge. Letters just say that I know something and you know something, but you cannot say that both something is common knowledge between both of us. So in general, as synchronous message passing is a little harder to implement. I mean, there's on machines, but we'll take a look at that in this lecture. On or off? Which one is this? Yeah. So the key thing which distinguishes asynchronous message passing from synchronous message passing is that there are two communication events, okay, a send and a receive, and they are both different. Okay. In the case of synchronous message passing, there is only one event which happens. Okay. So I say something, here I am saying something to you, that is the event which happened. Okay. So there's, of course you could break this down further and you can say, okay, I generate some waves in the air here and they get to your ear or something like that. So you could even say that this is asynchronous message passing, but usually we ignore this kind of small delays, okay, and we say that I say something, you are instantly receiving it. Okay. So, okay. So, but you can send a message without waiting. That's the advantage of asynchronous message passing. And synchronous message passing is like communicating with a phone or a web page. There is no separate sending and receiving. It's a bit like making a method call. Okay. It's one transaction which just happens. Okay. But the disadvantage is that even if you only want to send a message, you want to make a phone call and tell somebody something, you don't actually want to listen to what that person is saying, still you have to wait. You have to wait until that person picks up the phone, okay, and establishes the connection. There is no other. Okay. So programmers like asynchronous message passing. Okay. Basically because of you send a message and you forget about it. But then that message has to be kept somewhere in a buffer. Okay. So somebody has to implement that buffer for you. Okay. So and you just put your email on whatever, Yahoo or Gmail or whatever, right? But then Yahoo or Gmail has to maintain that message for you, right? Okay. So even spammers, they use asynchronous. So you get spam mostly through email. Okay. Even on your mobile phone, you get all these things as messages, right? All these advertisements that you get. Right. So there are relatively few people. I mean, I get, for instance, people from banks call me and say, do you want this credit card or something like that. But that's relatively rare because that person who is calling, if she wants to contact 100 customers, she has to actually call them, wait until that person is free, speak to that person. So it takes time. Okay. Whereas for sending a message, they don't have to do anything. Right. So we'll come to this example which we have seen earlier. The reason I want to do this is because I am taking this out of a textbook. Not the textbook I mentioned in the beginning, but there is another textbook, and there is a serious mistake in this textbook. Okay, and that's why I want to take this particular thing. I mean, I think what is being taught is wrong. So let me try to explain that. So, well, here is the dining philosopher which we have already seen earlier. So there is this table with the whatever spaghetti or noodles or whatever, and there are these 5 forks, and there are these 5 tables. Okay, and each philosopher spends life alternately thinking and eating, right? And a philosopher needs 2 forks to extract the spaghetti and eat. Okay, so now we want to implement this problem. So each fork is a thread, and each philosopher is also a thread. Okay, and we'll implement this using message passing. That's the idea. Okay. So here is fork extends thread, so it's a thread. Okay, it has some identity, so it's fork number 1 or fork number 5 or something like that. And there are 2 methods called pick up and put down, and there is a run method. And what the run method basically says is receive an instruction called pick up. Okay, right. So this is, of course, I mean, this is not Java, but we are going to implement this. We are going to implement this inside Java, right? So you receive a pickup message, and then later you receive a put down message. Okay, so this is what you want to do.